Nervous system, one important thing that nervous systems do is collect information from senses and then bring it to the central nervous system for processing or lead to a direct response depending on the situation. Now, of course, we have senses of our own that we're familiar with. There are many animals that have senses that we do not have. For example, echolocation. The range of sounds that we hear is much more limited compared to what a variety of other organisms have, such as the hearing range for many bats and dolphins, and there are certain other animals as well that are able to use sound higher pitched than what we can hear, and then heed the echoes to determine what the sounds are bouncing off of. So they can tell quite a lot about things, what sort of size and shape it is, where it is, things of that sort. In turn, sometimes the insects that the bats are after have ways of hearing that and then responding. So for example, in some cases a moth flying along hears bat echoes and stops flying, falls to the ground. It's small enough, it's not going to fall too hard, but that makes it a lot harder for the bat to find it. There's some that actually make sounds going back trying to jam the bat's echolocation. So there's quite a range there. Now, bats do not necessarily use this when they know what's around them. For example, sometimes people go into a cave with lots of bats and have a bat bumping into them, and then, oh, there wasn't a stalactite here last I checked. Better turn on the echolocation. And so bats know the way around their cave. They don't expect something to be there and aren't necessarily using it then, but then when one starts up and others, hey, Bob over there must have noticed something. I better check too. And so then they use that and are able to detect what's around them.
Echolocation. I find my prey, I find my way. Echolocation. I'm a little brown bat, hungry for a midnight snack.
Well, if you want to see the whole thing, the link's there. Bat in the ears, right? Okay. So, wide range of types of sensory systems. These provide lots of important information. May detect predators or other threats, finding food, finding water, finding a mate. What's the environment like? Is it too hot, too cold? All these are important pieces of information for living things. Different organisms detect different features, and then the brain has to put that together and form a perception of the world around. This perception, if you want to sound fancy, you can use the German term of Umwelt as what an animal's picture of the world around it is. And these are going to be different. Obviously, say for us, although we notice smells, it's not nearly the same as dogs do. Smell's a lot more important to dogs. Sight, not quite as much for them. And also smell differently. Dogs tend to smell individual parts of the mixture. We tend to appreciate smells as the blend of multiple things together, not picking out the individual components as much. So different organisms, the perception will be different. Of course, to sense something, you have to have some way of detecting it. So there are a variety of types of sensory receptors. These may be actual nerve cells themselves, and neurons, with special endings that are sensitive to various things. Or they may be other cells that do the detecting, and then these cells are able to transmit a signal to a neuron. Complex organisms such as ourselves have a variety of specialized sense organs where we have multiple cells working together to help detect signals and then process those and send them along to the nervous system. Several key steps are involved here. You first have to get the message. So you have to receive the sensory signal and take that energy as it comes in, whatever our source of signal might be, and change it into a form that's useful inside the body. For example, right now, your ears are experiencing vibrations in them coming from your speakers that derive from the sounds that I'm making. But wiggling in your ear is not particularly useful to the brain. And so that wiggling has to be turned into an electrical signal in the nerve, and then that transmits on to the brain. Okay, so we transduce it, turn it into the type of signal the body can use, transmit, send it on in, and then the brain, or other things that might be ganglion, whatever, has to take the signal and decide what to do about it. We particularly think of senses detecting what's outside, but we have sensation inside as well. And different types of sensors will detect a wide variety of different particular types of signals from what's around. This could be light, chemicals, vibrations, changes in temperature, sounds, one type of vibration, electricity, magnetism, gravity, any change in the pH, other dissolved things. These are key things, especially inside the body, but if you live in salt water, is the water salty normally? Or is there something strange going on? Temperature inside you, that's important to know. Where you are. Is there anything chemically in the blood that's not the right balance? These are important things that you need to know. And so you have sensory receptors detecting a lot of these. We don't have as much for some of them as certain other organisms do. Now, one thing, sensing also has to be regulated. Not all the signals coming in are of importance, and sometimes, well, you need to know it, but then once you know it, you don't need constant reminder. So, for example, say if you are currently sitting on a chair, you notice the touch as you sat on that chair, but once you've already sat down, you don't need your touch sensors constantly saying, "Hey, I'm still sitting." Guess what? You're still sitting. You're still sitting. Yeah, you know that. And you don't need your brain to be focused on, "I'm still sitting." It needs to be ready to pay attention to other things, like hopefully what I'm saying, or other things like that. And so, nerves tend to have an ability to respond adaptively and say, "Okay, yeah, I already got that message. I don't need to pay attention to that so much." This is quite important, say, in having a job working someplace kind of smelly, like somebody cleaning sewers. Pretty bad at first, but eventually your smell cells say, "I've already told the brain it stinks in here. I don't need to keep saying that." And so gradually you start to not notice the smell anymore. Or, other examples, say giant clams. They have symbiotic algae living inside their tissues. So a giant clam will sit there on a tropical reef in the Indian or Pacific Ocean, gaping open, letting the light come in, shine, so the algae get the light, and then the algae photosynthesize, and extra from that goes to the clam. But clam open means that some hungry fish, or for that matter person, can come along and take a bite. So if a shadow comes along, the clam closes up. But there are other shadows. For example, a floating stick. Floating stick going back and forth. Clam doesn't need to close for that. The clam is able to, this thing just seems to be floating back and forth, not doing anything in particular, and stop paying attention to that. Now, again, any one nerve, it's basically yes, no. So, telling the difference between different stimulus depends, one, on the sensory receptor, how it responds to what's coming in from the outside, and then the brain assessing what's going on. Each type of sensory receptor connects to particular neurons, transmitting that message onto the brain, and then the brain will interpret a message coming from a particular receptor as that type of stimulus. Now, of course, if for some reason something's stimulated not by its normal way, the brain's still getting a message from that same neuron and interprets it that way. A classic example of this would be the phenomenon of seeing stars when you get whacked. Among other things, if you're whacked in the face, that can trigger the neurons from your eyes saying something happened here. And the brain says, hey, I got a message from the eyes, I must be seeing something. And interprets that as lights. Now, of course, it wasn't really light that did it, but the brain takes that because that's what neuron it got it from.